Howdy, this is your friendly neighborhood physics teacher here, and we're going to talk about friction today. Hopefully, you did the Khan Academy little videos and activities, so you kind of got a grasp about friction, but I wanted to go over it just a little bit more to make sure we understand what's going on. So, friction is the main thing, is how two different surfaces interact. So, the saying, it takes two to tango, very much true in friction. You have to take both types of material into consideration. So, a few things that hopefully you'll be able to understand once this PowerPoint is over is you can identify which variables affect friction between the two surfaces. You'll be able to develop an equation that predicts the amount of friction between the two surfaces and differentiate between static and kinetic friction. And then, of course, recognize the importance of accounting for friction in real life problems. Like, what's the point? Why do we need to know friction? Okay, so we have a wooden, a wooden pallet that's on concrete. It's being pulled by a rope. So you have this force applied. So remember, we're doing kind of like a free body diagram here. The free body diagram just shows you what forces are acting on the object. So we have a force applied being pulled. So therefore, friction always goes against the motion. So if we're being pulled this way, that means the motion is that way. Friction always goes against the motion. So it always goes against the motion. So we have wood and concrete. Like I said, it takes two materials to tango. And even though it looks smooth, both surfaces do have some rough areas. And so that rubbing between those rough areas caused the friction. Now, one reason we have pallets is so we can load it up. Well, of course, my family, with me growing up on a farm, we would have pallets of feed. So we'd load it up with goat feed. And before we even, there was still always force of gravity, but now we have force of gravity. And of course, we have a force of normal. Now, force of gravity and force of normal don't necessarily affect the motion because remember, forces in the y direction do not affect forces in the x direction. Now, if we change the material we're dealing with here, so now we're no longer wood on concrete, we're wood on ice. So as you notice, ice is, we've all walked, well, I wouldn't say all, but hopefully, maybe you've experienced walking on a slippery surface, and it's not fun because you don't have the grip that you need. Even though if you have rubber soles, they're made to grip, or like hiking boots that's supposed to help grip onto the rocks and stuff. There's not much grip on a slippery surface, especially like ice, which we might be seeing Wednesday, Thursday this week. Okay, so basically what's happening here is that friction, so the different rocky edges of concrete and wood, is preventing the pallet from moving. You can sit there and pull and pull and pull and pull. And what you have to overcome is called static friction. Think about the word static means not moving. So this is the friction that keeps the object from moving. You actually have to overcome that type of friction before you can get an object to move. And then it goes into kinetic friction. The word kinetic means movement. Hence our first unit was kinetic motion. So once you get it to move, then of course, um, it's a whole lot easier. If you ever sit there and try to push or pull a really heavy object, once you get it moving, it seems like it's a whole lot easier. And because it is, your kinetic friction is always less than your static friction. So, static friction is the force which must be overcome to um, initiate your movement. Oops. Your kinetic friction is a force which must be overcome to maintain the movement. So, static friction, you have to get it to move, then you have to overcome the kinetic friction to keep it moving. That's why when you're pushing something heavy, you don't want to stop pushing because then you have to do extra work to go over, back over, dealing with the static friction to get it moving kinetic friction again. Okay, so this is something you might see in a lab. I have a lab table, piece of wood, a string, we have some mass on it. So again, F equals ma. This is just F equals ma. It's just written a little bit differently. This way is actually how you see it on your formula chart. So if you go grab the formula chart or pull out your formula chart, this is what you see. It's just F equals ma written for acceleration, which just manipulate it. But this is what you see on your formula chart. So I'm going to start using that a little bit more to get you used to it. So as you start pulling, you have this force of friction. Now, if you notice, I want to go back a little bit. If you notice, as you start pulling, the friction stays equal until something happens, you overcome that static friction, and then your kinetic friction automatically jumps down. So it's at the beginning, it's balanced because your forces are the same on each side until it overcomes that static friction, and then you can actually move the object. So again, so static friction is 2 newtons. You will sit there and pull for a certain amount until it overcomes. So, so your friction is 0 newtons. Let's watch that again. So it's 0 newtons. Back up. Thank you. Okay. So it's what we're pulling starts at 2. He's pulling at, so your force is, because he's pulling at 2, it's not moving, your force of friction stays at 2. As he pulls to 3, again, your force of friction stays to 3. Sorry, it jumped down to 1 and had a little glitch there. So this is your static friction. Now, for your kinetic friction, so the maximum force of friction, you're going to sit there and pull and pull and pull and pull until, again, it overcomes. And so your static friction is 4. That means you had to overcome that force. You have to pull it more than 4 newtons to make it move. Now, once it starts moving, it drops down to 3 because your kinetic friction is always less than your static friction. So that's why your static friction is written equal or less than 4 newtons. So your static friction can literally be anything from 1, well, technically 0, but it wouldn't be, so point, we'll just say 0 to 4. Your static friction is never greater than 4, but your kinetic friction is 3, so that's not a greater, just what it is. Now, if we increase the amount of mass on it, so if we're increasing the mass, we're increasing the force of gravity, so we're increasing that force in normal, that's going to end up increasing our friction. It's going to increase our friction. So if we increase our force of normal, we increase our friction. So force of normal plays a big part in our force of friction. We do it again. We're increasing the mass, which increases the force of gravity, which increases our force of normal. And again, our force of friction, static friction goes 12, and then kinetic friction goes to 9. So our maximum static friction versus our maximum kinetic friction. So friction is affected by our force of normal. Friction is affected by our force of normal. You will see force of normal in your force of friction equation. Now, if we change materials, so again, remember it takes two to tango. If we change materials, it's going to change your static friction. So ice doesn't take very much friction to make it move. Wood, glass, no friction. Of course, you have rubber or granite, it's going to take a lot of friction for it to move. So this is our equation. This is how the equation is written on your formula chart. Your force of friction is less than or equal to, and the reason you do that is because for static friction, mu times your normal force. Now, what is mu? Mu is that lovely, funky little U with a front tail on it. It's a Greek letter, and no, it's not like the Pokemon. And technically, yes, you have absolute signs on there, and this is the reason you have to do that is so you can get a force in the x direction to interact with a force in the y direction. And you have, again, just a better look at your equations here. So again, your static friction, you deal with your coefficient of friction for your static, and then for your kinetic, you deal with your kinetic. Now, basically what this mu is how these two surfaces interact. So this is a constant. So your mu is a constant. There's all kinds of crazy constants. So basically, what the graph would look like, it would go steady, getting your static friction for any object would be getting stronger and stronger and stronger until you get to that breaking point. When it starts moving, it will quickly drop down and then stay constant. That's why you have a less than or equal to sign for static, and then just equal to on your kinetic friction. This little slurp here happens so fast that we really, in physics 1, we don't really pay attention to that. So that's why you could just say it's equal to. Now, these are all your different mu's. So different materials like aluminum and aluminum. And of course, you have to think about, is it a clean and dry, or is it lubricated and greasy? All kinds of stuff affects that thing. And you can just keep going. This is from copper, and then go diamonds, and then, and just keeps going and going and going. And, this is alphabetical. It is. We're finally to Z. Now, MI and even AP is not this evil to make you memorize all these. It's not. They're constant, and it's constant for any two types of surfaces. They could throw any two types of surfaces out there. So either A, you will be given your coefficient of friction in a chart like this that you have to find, or they would just give it to you, or B, that's what you're looking for. So do you have to memorize all these? No. I repeat, so no one can go say that I had to memorize all these. You do not have to memorize all these. I just wanted to show you that there's all kinds of craziness out there. Now, we have how hard must you pull to get the sled to move? So our materials, we have a waxed skis and snow. This is dry, static is 0.1, coefficient is 0.5. So if we were looking at your static friction, so we have 350 pounds. So pounds, remember, is already, that is the English version for equivalent to newtons. So it already tells you it's force of gravity, which in this case, it's not on a tilt. So force of gravity equals your force of normal, as long as there's no incline. So you can just plug that in to your force of normal, and then your static coefficient goes in there. And you just multiply the two together. So the friction that you have to overcome to make this sled move is 40 pounds. So how hard to keep the moving sledding? So you have to pull 40 pounds to get it to move. But once you get it to move, how much do you have to pull after it's moving? Hopefully it's less. That's the whole idea. Your kinetic friction is always less than your static friction. So again, you do your force of normal doesn't change, because again, force of gravity equals force of normal as long as there's no incline, and then you just use your static. So it takes less. So once you get that initial pull, you can drop it down a little bit. So your static friction is always greater than your kinetic friction. I've said this 100 times already. Well, not quite. I'm over exaggerating. But this is very important. So if you haven't written down this in your notes yet, please do. So the coefficient of static friction is always greater than the coefficient of kinetic friction. Kind of important. Okay. So is this static friction or is this kinetic friction? I'll let you see that one more time. Hint, it's a trick question. Okay? So then I'll let you. So that's going to be static. The reason it's static is because it's rolling. This part here isn't sliding, it's sticking. And since the object is made to roll, it's causing, so it's sticking, but because of inertia, the object is still moving, so it just causes it to roll. Now, in this case, that will end up being kinetic. The reason it's kinetic, again, it's sliding across the two surfaces. So anytime you're skidding in your car, that's kinetic. Anytime the car is moving properly, that's static. To have friction, you have to have something sliding against. So it takes more effort to keep. That's why you skid on icy, wet roads. That's why your wheels do that, because there's not enough friction to keep the wheel from moving. Friction drops too much, it's not going to be holding. Okay. So a car in front of you suddenly slams on its brakes. You need to stop quickly. You say a four-letter word. Now, this is a physicist yelling a four-letter word, so of course you yell friction. You need friction to stop. Well, you can yell a four-letter word. Starts with an X. Oh, come on, get your mind out of the gutter. You know I was talking about physics. Hee hee. Okay. Silly time's over. Let's focus. So again, your static friction will always be greater than your kinetic friction. You have to overcome that, and it drops back down. So again, like I said, your coefficient of friction will either be A given to you or something you have to solve for. In this case, that's what we're calculating. So it's being pulled at 13 newtons. So this is our force applied. This is our force of gravity. Is it on an inclined plane? Kind of looks like it is, but the answer is no. And so our force of gravity equals our force of normal. We're looking for our mu. So you can go ahead and manipulate. All I did was divide both sides by force of normal to get our mu, the force of friction, divided by force of normal. The object's moving. So it's moving at a constant rate. It was not speeding up, was not slowing down. So force applied, force of friction. So we can plug in force of friction. We know that force of gravity equals our force of normal. So we can just do 13 divided by 15. And you get a 0.87. If you notice, most frictions are decimals. And another thing to also notice, I always fuss at no negative numbers running around. Your coefficient of friction has no units. Your coefficient has no units. Just think about it. This is force of normal. This is force of normal. Not force normal, sorry. This is Newton. So it's a force over a force. Your newtons cancel out, left with no unit. So the free body diagram in this case would be your weight or force of gravity, your force of normal, your force of friction, and your force applied or force of pull. Now, your force in this case, your force applied equals your force of friction, so they should be the same magnitude, and your force of normal equal your force of gravity. So again, they should be the same magnitude. Magnitude just means length of the vector. Okay, so now we're going to take it a step further. That was just trying to figure out force of friction. Force of friction is just one, or force of dealing with friction. So now we're going to use it as a whole. And oh, look, we have an angle thrown in there. Why? Just because. Okay, again, we're still adding numbers. I know I said we were going to take away numbers soon. I will do that soon, but we're still learning about a new force, so we're going to keep the numbers in there for right now. But we're going to calculate the acceleration of the whole entire system. So again, it's being pulled at an angle. It's not at an angle. So this is what we're looking for. We're looking for the acceleration. So we need to figure out the net force. Now, which direction is it going in? Is it going in the y, which would be up and down, or in the x, which is horizontal? Hopefully you said x. So we're going to focus on forces that are in the x direction. So our force of gravity is mass times acceleration due to gravity. Our force of gravity is 15, but we need to figure out the mass, right? So we can plug in 15 equals mass times 9.8. 9.8 is the acceleration due to gravity. To get the m by itself, you're just dividing both sides by 9.8. And so you get your mass to be 1.53. Now, our force of friction. Now, it is accelerating, so therefore it's moving. So we need to find the kinetic. And also, again, I gave you the coefficient for kinetic friction, but you need to figure out your kinetic friction. So in this case, it's not on an incline, but our force of normal is going to be a little bit harder to solve for, because we need to break down exactly, because in this case, we have one force going down, but we have two forces going up. We have a force of normal and this force applied in the y. So we're going to use sine and cosine to figure out our force applied. So this is our force applied. This is our force applied in the x. This is our force applied in the y. And so therefore our force of normal is just going to be our force of gravity minus our force applied in the y. Where that comes from, let's see here. Okay. Where that comes from is the net force in the y. So the net force in the y, we have force of normal going up plus a force applied in the y. I'm running out of, what was I add a little bit more. Net force in the y equals force of normal plus force applied in the y minus force of gravity, right? Well, it's not moving in the y direction, so our net force is going to be 0. We're looking for our force of normal plus our force applied in the y, we figured out to be 6.18 minus our 15. We do a little bit of manipulating there, and you get that the answer is 8.82 newtons. So basically what we did, negative 8.82, we just brought it over to get 8.82 equals force of normal. So now that we know what force of normal is, we plug that here. We know what our coefficient of friction is. We just multiply those two together. So then the forces that are in the x direction would be your force applied in the x and your force of friction. So force applied in the x minus your force of friction divided by your mass. Voila! You get that it's moving at 8.04 meters per second squared. So yes, again, like we were doing on the board or previous videos, it's not, each step isn't a lot of work. It's just a lot because there's a lot of little steps. You're either just multiplying, subtracting, adding. I mean, it's your sine and cosine's most complicated math in this part. So in this case, your free body diagram, you would have your weight, which again is just your force of gravity. You'd have your force of normal. Now, your weight should be greater, like if you're drawing, your weight should be greater than your force of normal in this case, because your weight, or your force of gravity, has to equal your force of normal plus your angle, your force applied in the y. And you have your force of friction and your force applied. When you're doing a free body diagram, though, you do not break it down to its x and y components. It's just purely your basic forces. You only break it down when you start doing the math. So in this case, you have a person pushing at an angle, and again, your friction always goes against the motion. You have your force of weight, or just weight, and then your force of normal. The reason your force of normal is greater than your weight, again, your force of normal has to be balanced out by your weight plus whatever force or push you're pushing down. Now, so we've dealt with objects being pulled at an angle, so now let's see what happens if an object is rolling at an angle. So you have your force of gravity, and I've given you your angle. We've already broken down your force of gravity in the x and force of gravity in the y. So this is your force of gravity in the x. It is, force of gravity in the y. That is your perpendicular. This is parallel, so that's your force of gravity in the x. X and y. So how much force would you have to be pushing to make sure the ball doesn't roll? To balance out would be 34. You're absolutely correct. Now, so that's what that 34 means, is just how much force you would have to be pushing to keep it from rolling. What that 67 is, if you weigh yourself on an incline, you're not going to get your full weight. You're not, because gravity always pulls straight down. So since your normal force is kind of tilted a little bit, you would get what you put on the scale would be 65 pounds instead of the full 75 pounds. Okay. So will the box slide? It's just a question. Will the box slide? Again, we've already broken down our x and y components. So this would be our force of gravity. So this is our force of gravity in the x. This is our force of gravity in the y. I'm telling you your force of normal. So this would be your force or normal. Remember, force of normal is always perpendicular to the surface. So your force of normal is 67. And we need to figure out our force of friction. So we have force of normal. I'm telling you our static coefficient of friction is 0.4, so you just plug it in. And so if that 34 overcomes 27, which it does, then the object would be, so that's all extra stuff. So this overcomes that, so guess what? It does move. And again, you have your weight, which is just another force of gravity, your force of friction, and your force of normal. Now, let's say it's a box that's made of a different material, so still same mass of the box, so same force of gravity, everything. This is still force of gravity. This is still your force normal, still your force of gravity in the x, still your force of gravity in the y. But your coefficient of static friction changes. So now your force of friction, static friction, is 38. Does the object move now? Hopefully you said no, because your force of gravity in the x doesn't overcome your static friction. In theory, it would slide up if that was possible, if you had like a string, but if not, it would just stay still. Okay. So I want you to draw a free body diagram, calculate the coefficient of friction of the box just begins to slide at an angle of 28 degrees. The mass of the box is m. The weight of the box is m times g. Hint, I'm taking away numbers now. No more numbers. We're just using variables. Again, remember, variables are the letters that are in the equation. So, I know, I'm about to be mean, but I need you to get used to this. So, we have an object that has an angle of 28 degrees. So we have mass times gravity, acceleration due to gravity, which is just our force of gravity. We're breaking down the force of gravity into the force of gravity in the x, force of gravity in the y. So your force of gravity in the x is just your force of gravity sine of 28. Force of gravity in the y is just your force of gravity cosine of 28. If the object doesn't move, it's balanced, then your force of friction is going to be the same. So what did I ask for? Let's backtrack a little bit. I asked for the coefficient of friction. Well, I didn't state static or, well, that's my fault. So if you're looking for static friction, it's going to end up being the same. Be specific and put static friction. Now, your force of normal is going to be the same as your force of gravity in the y because it's not moving in the y direction. So force of normal equals force of gravity in the y, and your force of gravity in the x equals your force of friction as long as it's static. So remember, we're looking for our mu. Masses cancel, gravity cancels. So you're just left with, and once you do a little bit of geometry there, I'm simplifying. You can do sine of 28 degrees divided by cosine of 28 degrees. That's all I did. So I divided both sides by cosine of 28 degrees. Simplifies to tan, or you could just plug it in and get a number. Maybe not, but apparently I don't solve for it. You can get a number. Now, since gravity cancels out, it doesn't matter if I do this project on Earth, on the moon, on Mars, it doesn't matter. Your coefficient of static friction is still going to be the same since gravity gets canceled out. It doesn't matter if you have a huge box or a small box because mass gets canceled out. If it's at that same angle, you're going to get the same static friction as long as you're dealing with the two same objects. Okay. So a couple of things. So that's end of the PowerPoint. So it's end of the PowerPoint. So a couple of things I want to make sure you got clear. So we have two different types of friction. We have static friction and kinetic friction. Static friction is what you have to overcome to make it move. Kinetic friction is what it's moving. Now, if we have an object, we have force of gravity, force of normal, force applied, and force of friction. In this case, force of normal would equal our force of gravity. We know that force of gravity is always mass times acceleration due to gravity. That's on your formula chart. It's actually written like this, though. That's how it's written on your formula chart. But that's on your formula chart. So you know that your force of normal equals mass times acceleration due to gravity. And this is your dealing with your net force in the y. Remember, anything up and down is in the y direction. Dealing with your net force in the x, you would have net force equals mass times acceleration. Our forces, you'd have a force applied minus your force of friction equals mass times the acceleration. That's kind of talking about what type of force of friction you're talking about. So if it's static friction, is the object moving? Hopefully you said no. Not moving. So if it's not moving, what does that make your acceleration? Hopefully you said 0. So that would make this whole entire thing 0. So it would be that your force applied equals your force of friction in the static. Now, if you're dealing with force applied minus your force of friction in the kinetic, kinetic means moving. So it is moving. So you would have to go through, sorry, you don't have to stop here. We have our force of friction, which would be our mu, force of normal, and we can even take it a step further because we know what our force of normal equals. So it'd be our force applied equals mu times mass times gravity. So we can simplify it that far down. Our force of friction is mu times normal force. So that's plug that into there. And then we solved normal force up here. No. So we were able to fill that to there. That arrow should go down to there. Now, for our kinetic, it takes a little bit more manipulating. So again, our force of friction is our mu, in this case our kinetic mu, times normal force equals mass times acceleration. Again, so our force of friction kinetic equals mu, almost looks like an M, hold on, mu times normal force. So that gets plugged into there. Our normal force is the same. So we get our force applied equals mu kinetic times mass times gravity equals ma. Now, before you get cancel happy, can't cancel it just quite yet. Can't cancel it actually at all because we don't have an m in each thing. So if we're looking for a force applied, we need force applied by itself. So we're going to add our mu times normal force times g to both sides. And the reason we're adding is because of this right here. So all that cancels, and we get a force applied equals mass times acceleration plus mu k mass times gravity. And you can manipulate for anything. If you're looking for your coefficient of friction, if you're looking for your mass, you can sit there and manipulate for anything. So there you go. So you can plug in and simplify. That's what I meant by plug in and simplify. We'll go more into this next time. If you have any questions, at this point in time, I'm going to slowly be easing um, out of being as accessible as I need to. So if you have questions, please message Miss Verona or Miss Casanova. They are both on CTC. I know that doesn't really help my Fort Hood people, but you can message them on Schoology. They will be added to the Schoology page as well. Um, Hopefully, y'all are doing well. I miss y'all very much. Remember, you're loved and appreciated. Bye.